Hello, everyone, and thank you for joining us at day 2 of DeveloperWeek Cloud 2022. Up next on the Expo Innovation stage, we have Sean, Head of Product at TDengine.
Thank you, Garrett. Okay. Good morning. My name is Sean Ely. I'm the Head of Product at TDengine. My presentation today is on how to handle 1 billion time series in real time. So for those who don't know TDengine is an open source time series database, purpose-built for IoT. TDengine was first open source in 2019. Its cluster edition was released in 2020, and last month we released our cloud native edition. Cloud native will be released this month, next week. TDengine is a very popular open source time series database with over 19,100 stars on GitHub and over 150,000 running instances in over 50 countries. TDengine is built for developers. It provides a simple solution for time series data processing and storage. TDengine is a time series database with caching, data subscriptions, and stream processing. By having built-in time series data processing, TDengine can reduce the system complexity and operational costs significantly. The diagram on this slide shows an all-in-one solution where solutions like Redis and Kafka can be used, but they're not required. So in a report by the International Data Corporation, it is expected that the number of Internet of Things, IoT devices, around the world will be more than 41.6 billion by 2025. During this time, these technologies are expected to see a compound annual growth rate of 28%. All told, according to this report, IoT devices will generate approximately 79.4 zettabytes of data in the next 5 years. A zettabyte is equal to 1 trillion gigabytes. There's a lot of data, and the growth of data is exponential, not linear. So when real-time data scales to billions of time series, this presents some interesting challenges. How do you handle the volume of metric data? This could be hundreds of terabytes of data every day that needs to be processed and stored. For example, smart meters generate around 112 terabytes of data every day in the US. How do you handle the metadata associated with time series data? To be useful, data needs context, and metadata needs to be stored with the time series metrics. A billion time series would typically have more than 1 billion labels. Finding and aggregating data at this scale is a big challenge. How do you guarantee the query latency? This can be a challenge both in terms of usability and in terms of system performance. Running a complicated query, you don't want a performance degradation for ingestion. As you may have guessed from the last slide, to handle 1 billion time series in real time, you need a distributed solution that can scale horizontally. For TDengine, you can install locally, you can install in private or public clouds, or you can use our hosted version. To fully utilize the benefits of cloud platforms, time series databases must also be cloud native. To achieve this, they need to be redesigned with the following 3 points in mind. Separation of compute and storage. In containerized environments, specific containers may be up or down at any time, but stored data is persistent. Elasticity. The system must be able to adjust storage and compute resources based on workload and latency requirements. For compute resources, this is not a hard decision for the system to make. But for storage resources, this is another story. To scale a distributed database up or down, its shards have to be merged or split while live data is coming or querying or queries are running. Designing a system that can accomplish this is no easy task. And Thirdly, observability. The status of time series databases must be monitored together with other components of the system. So a good database needs to provide full observability to make operations and management simpler. So let's take a look at how TDengine separates compute from storage. At a high level, a working system must have at least one data node in our architecture. This is abbreviated as D node. One or more data nodes form a cluster. To interact with that cluster, an application connects through the connector API, which is shown on the left and abbreviated as TAUC. Each data node is virtualized into multiple virtual nodes to better support sharding and load balancing. A virtual node contains a certain number of tables, and in addition to the stored time series data, it also saves the schema and label values of included tables. The management nodes are responsible for maintaining and running status of the data nodes and for load balancing. We also introduce in our newest version a query node, which separates some of the more difficult compute tasks. So the query nodes run query calculation tasks. When the query is executed, depending on the execution plan, the scheduler will arrange for one or more query nodes to execute it together. Inside each virtual node, data is partitioned on two dimensions. Data is sharded based on time series, with each shard containing data for multiple time series. And data is partitioned based on time ranges for each shard. A virtual node may contain multiple shards. One of the functions of the management node is to load balance the virtual nodes. To do this, each data node represents its status, reports its status storage, memory, CPU, active virtual nodes, etc., to the management node through a heartbeat every second. And the management node saves the state of the entire cluster into memory. The management node evaluates its load status according to the last score of each data node. When a new data node is added to the cluster, the load score starts at 0. When the management node finds the load of the data node is too high, it will instruct the data node to migrate one or several virtual nodes it contains to other data nodes. Data sharding is done at the virtual node level. Each virtual node contains multiple tables. The data of a virtual node is only stored on a single data node. When a virtual node in the system becomes a read-write hotspot, the virtual node is split. The split strategy is first add copies, then adjust the hash range, and finally delete the redundant data. When trying to handle the metadata for a Boolean time series, you run into an issue of high cardinality. Broadly defined, cardinality refers to the number of values in a set. Sometimes the cardinality of your set is small, which we call low cardinality, and other times it can be large, which we call high cardinality. In the world of databases, cardinality refers to the number of unique values contained in a particular column, field, or database. With time series data specifically, things get a bit more complex. Time series data tends to be paired with metadata, also called tags or labels that describe the data. Cardinality of the time series data set is typically defined by the cross product of the cardinality of each individual tag. So if we have 100 million devices, we'll have 100 million set of tags, and each set will have a couple to 100 values. And each value will have its own level of uniqueness. This quickly poses a large issue when trying to aggregate and filter data in a large data set. It can cause significant latency. This is what's called the high cardinality problem for time series databases. So how do we solve this problem? Our answer is a distributed design for metadata processing. The previous versions of TDengine stored metadata all in memory in the management node. This worked very well, but when scaling, it created challenges in controlling memory usage, and on startup, all metadata needed to be loaded into memory. The newest version of TDengine stores metadata only in the virtual nodes. Now the management nodes only store node, user, and database information. To address the sharding of metadata, B-tree is used to structure the metadata, and consistent hash is used to find the node directly via the table name. By moving the metadata out of memory, TDengine solved the issue of slow restarts and managing large data sets with limited memory. In separating the compute from the storage in the virtual nodes, the newest version of TDengine introduces a query node. For simple queries like select all, sum, or count, the data is returned from the virtual node directly. More time-consuming queries, such as merging, sorting, aggregating, are performed in the query nodes. Query nodes are dynamically started and stopped by the management node. This separation of compute and storage reduces the impact on performance when complicated queries are run and enables TDengine to ensure a short latency. So far, all the capabilities I've been talking about are available in our open source solution. TDengine will also be releasing a fully managed solution on AWS, Azure, and Google Cloud next week. Our cloud offering has all the great features of our cloud-native open source solution, plus a simple and clean interface and some very useful features like multi-cloud replication, VPC peering, and IP whitelisting. In this presentation, we talked about TDengine's cloud-native distributed architecture, addresses the challenges of scale, elasticity, and performance. We talked about how moving the distributed design for metadata can address the high cardinality issue. We talked about how splitting storage and compute through the introduction of the query node allows queries to scale without affecting real-time data ingestion. And finally, we introduced TDengine's fully managed cloud service. Thank you everyone for your time and attention. Please feel free to scan the QR code to add me on LinkedIn. And I will open up the session for any questions or discussion.